This is video 2 for Physics C Mechanics differential expressions. We'll start off with I equals the integral of r squared dm for moment of inertia. And of course, torque equals r cross f. It should be r cross f is better. That way it gets the same signs that we have in our physics textbooks. Torque equals I alpha, of course. Therefore, torque equals the second derivative of theta with respect to time. Power also equals torque times omega, which means torque times d theta dt. So that way you can easily get an expression in terms of theta and time. Very similar to power equals force times velocity. Next, dw, of course, the derivative work does equal torque d theta. Just like dw equals force times ds. Now what about our moment of inertia equations? Well, the rod, of course, to get mass, we use lambda equals m over L, which is the linear density. Okay, and of course dm equals lambda dl. Disk, we use sigma, which is mass per area, so I call that the area density. And then dm equals sigma dA, and dm equals sigma 2 pi r dr, assuming that area is equal to pi r squared. So we remember that there is a parallel axis theorem. I parallel equals I center of mass plus md squared. And d, of course, is a distance that the point of rotation is from the center of mass. Now what about net torque? Torque does equal I alpha, of course, the net torque. But torque also equals the change in angular momentum with respect to time. Just like force, okay, had a relationship with linear momentum and time. So does torque. Let's continue. Finally, with our simple harmonic motion equations, of course, force equals minus kx. Then we have ma equals minus kx. And then dividing m to the other side and substituting the second derivative of x with respect to time and for acceleration, we have the general form for simple harmonic motion, which is a second order derivative of x with respect to time equals a minus constant times x. Angular frequency then equals the square root of k over m. And our x sub t equation equals cosine wt plus angle of phase shift angle. Now, of course, we can also use sine with that in a phase shift angle, depending on where your motion starts from. Thus, torque equals minus k alpha, or theta. Okay, that's for the angular equivalency. If we look, we have minus force equals minus kx. Now we have torque equals minus k theta. And of course we have I alpha for torque equals minus k theta. And alpha equals minus k theta over I. And now we have a second order derivative of theta with respect to time equals minus k effective over theta. Now we're calling them k effective to make it a little bit more general term than just simply force being constant. Our angular frequency W equals the square root of k effective over I, very similar to our linear equivalency over there. Okay, finishing up, remembering frequency equals omega over 2 pi, therefore T equals 2 pi over omega, which is our angular frequency again. So this gives us our linear frequency, and this gives us the time that we can calculate, okay, for one period. Those are our different